We are going to start Chapter 5 today. Section 5.1 looks at the areas between curves. If you do have graph paper, there's a lot of graphing involved for every example we do here. I would recommend doing this on graph paper. So we're actually going to look at this two different ways. The first, we're going to look at the area A of a region bounded by the curves y equals f of x, y equals g of x, and the lines x equals a and x equals b. Those will be two vertical lines, where f and g are continuous functions, and f of x is greater than or equal to g of x, meaning that curve sits above the other curve. F of x will sit above g of x, or right at. For all x in the closed interval a to b is this integral below. Now keep in mind, we are looking at area, so we're going to have to put square units after all of our answers. So what this statement is saying is we're looking at a curve that sits above another one. Our last two examples, we're going to see curves that could sit to the right of a curve that's going to be to the left. So we're going to have two different directions ultimately. And this is just our choice if it's a little bit easier to look at it in one direction than the other. So pause the video if you still need to copy that down. All right, also pause the video again to copy down this problem. We're going to find the area of the region bounded above by y equals x squared plus 1, bounded below by y equals x, and bounded on the sides by x equals 0 and x equals 1. So notice when I go to draw my coordinate plane, I want to kind of space this out a little bit because we're just going between 0 and 1, so I want to show enough space and not make the graph look too small. All right, so let's first go ahead and graph y equals x squared plus 1. That is a parabola whose vertex is at 0, 1, so it's just the parabola shifted up 1 unit. Now if I go over 1, I'm going to go up 1 squared, or if you just substitute in a 1, 1 squared plus 1 is 2. And if I did want to go over to 2, 2 squared plus 1 will bring me up to 5, but I don't really need to go over that far. But this is the curve I'm looking at. For y equals x squared plus 1. Again, I'm just going between 0 and 1. And then the other is just a line, y equals x. So I have a y-intercept of 0, 0. And then we have 1. And then we have 2. All right, so then I just want to draw in the vertical lines x equals 0. And then x equals 1. And I'm going to shade in the area bounded by these 4 curves, lines, which is right here. So right here, this is y equals x squared plus 1. Notice how it sits above the line y equals x. So I'm just trying to find the area of the green region. So if you recall, we're going to use integrals to help us find this because this is not a nice geometric shape. So my area is equal to the integral. I'm just going to go back a page. We're looking at this right here. So we're going to have the area is equal to the integral from a to b. That's going to be our 0 to 1 of our curve that sits higher up minus the curve that's below it. So area is going to be the integral from 0 to 1. The curve that sits above this is x squared plus 1 minus, and because if it ever was a binomial, we have to put it in parentheses. The curve that sits below is just y equals x, so we just put in an x here. So right here, this is f of x minus g of x, and then dx. All we do is now calculate this integral. All right, so pause the video, go ahead and do this. It's just good practice for everything else we've been doing throughout Chapter 4. This is really the only difference. We have to make a sketch of our curves, shade in the area, set up the integral. After that, That's stuff that we've been doing for a while. So pause the video, evaluate this, see what you guys come up with. All right, so if we take the antiderivative of each term, we are first going to get an x cubed over 3 plus x minus x squared over 2 from x equals 0 to x equals 1. So substituting in the 1, we're going to get a 1/3 plus 1 minus 1/2, technically minus a 0. We get common denominators just of 6. We'll get 2/6 plus 6/6 minus 3/6, which ends up giving us 5/6. And because this is area, we say square units. And that's the basis of these problems. Okay, let's try another one. Again, pause the video to copy this down. We're going to find the area of the region enclosed by the parabolas y equals x squared and y equals 2x minus x squared. Now the first one's going to be easy to graph. The second one we have to do a little bit of work off to the side to graph this. But again, once you're done copying this down, go ahead and set up a coordinate plane. And it's always good, just like I did in the last graph, to label the two curves. So first let's start with just y equals x squared. So that's just the parent function. Now I'm going to draw enough of this because notice it doesn't give us two vertical lines. So we have to kind of see how the graphs present themselves and where to go from there. So if I have y equals x squared, again, if I go over 1 up 1, over 2 up 4, if I go over to the left, over 1 up 1, over 2 up 4, so this is my parabola here. All right, so now let's take a look at y equals 2x minus x squared. To help us graph this, let's go ahead and figure out the x-intercept. So I want to set this equal to 0. I want to factor out an x. So my zeros are going to be x equals 0, and then x equals 2. So I have an x-intercept here, and an x-intercept here. If I were to just write this in order, this becomes y equals negative x squared plus 2x. So this is a parabola that's going to open down. And then I could find my vertex. So my vertex is going to be hk. So h is equal to the opposite of b over 2a. So in this case, b is 2, so I'm going to get a negative 2. A is a negative 1 right here, so 2 times negative 1. So this gives me negative 2 over negative 2, so it's a 1. And then when I go to substitute a 1 in here, at h equals 1, k is going to equal the opposite of 1 squared plus 2 times 1. So this gives me a negative 1 plus 2, so that's also a 1. So my vertex is at 1, 1. So I can go ahead and put a point right here. And then I know that this will open down. All right, so we could see where this graph, this area is going to be bounded by. So notice right here, still between 0 and 1. But I had to get that graph to show that. Another thing that we could have done was set these two equal to each other to figure out where they intersect. So we could say find the points of intersection. So this is always good to do, just in case our graph doesn't look that accurate. If you didn't use graph paper, we have to be sure what our boundaries are. So all we'd have to do is set x squared equal to 2x minus x squared. Let's bring everything over to one side. So we're going to get a 2x squared minus 2x equals 0. Factor out a 2x. So if 2x is equal to 0, then x would equal 0. And x minus 1 equals 0, x equals 1. So these are actually the x values of the points of intersection. So that's how we know where to go from 0 to 1. All right, so we labeled our two graphs. So now we're going to set up our integral. So area is going to be the integral from 0 to 1. What do you think the curve we're going to write first? Remember, it's the curve that's above, bounding the area on top, minus the curve that bounds the area below. So in this case, this green curve, so the 2x minus x squared is going to go first, minus the curve that's blue here, that is the x squared. Now we could simplify this before we take the antiderivative. So we get 2x minus 2x squared. Again, pause the video, go ahead and evaluate this integral. All right, so let's see what you were coming up with. So if we take the antiderivative of 2x, that could just give us 2x squared over 2, which will just turn into an x squared. Then we get minus 2 times x cubed over 3 from 0 to 1. Now you could have also factored out a 2 and just put it out in front, but we get x squared minus 2/3 x cubed, again from 0 to 1. So evaluating now, we're going to get just 1 squared is just 1. 2/3 times 1 cubed is 2/3. And then still just a minus 0 if we substituted 0 in. So we should just be ending up with a 1/3. And again, it's area, so square units. Right, this next one involves the graphs of y equals sine x, y equals cosine x, x is equal to 0, and x is equal to pi over 2. So please copy this down. Now, because we're looking at y equals sine x, y equals cosine x, I'm not going to number the x-axis by 1, 2, 3, or 4. We have to do pi over 2. That's pi, and then I think we could just go up to pi. That should be good enough here. Then I'm actually going to count 4 up for 1 and then 4 down for -1. All right, so graphing y equals sine x. If you remember, that goes through the origin. The sine of 0 is 0. Sine of pi over 2 is 1. And then sine of pi, we're back to 0. So we get a curve that looks like this for right now. And then y equals cosine x, we start up at 1. And then cosine of pi over 2 is 0. Cosine of pi is -1. So we get a curve that looks like this. So let's label these. This is y equals sine x. This is y equals cosine x. All right, so now graphing the vertical lines x equals 0 and x equals pi over 2. There's x equals 0. X equals pi over 2. So here's the area we're looking for. So we are right between the red and the green here, and then over here as well. So we have two sections. So this will be best set up with two separate integrals, because if you notice from this first part, The red curve is above the green curve, so cosine x sits above sine x. But as soon as we cross that point of intersection for them, sine x sits above cosine x. So we do still have to find the points of intersection, at least the x values. And it's just the one, so x value of point of intersection. All we're going to do is set sine x equal to cosine x. Now, we really can't solve this algebraically. This will just be helpful to know we're in the first quadrant. We're between 0 and pi over 2, so we're in the first quadrant. Where is sine x equal to cosine x? At what radian measure are the two values of the ordered pair the same? So this happens at x equals pi over 4, right in the middle. And that looks like it right here. Looks like we're right in the middle at pi over 4. So this is going to help us separate our two integrals. So area is first going to equal the integral from 0 to pi over 4. And again, this is where cosine x sits above sine x, so we want cosine x minus sine x dx. Then we're going to add that to the integral from pi over 4 to pi over 2. But now sine x sits above cosine x, so we want sine x minus cosine x dx. So hopefully the setup makes sense. Everything else is stuff we've been working on before. Let's go through this together. Unless you want to try it, pause the video, go ahead and give this a try. All right, so first we need to take the antiderivative of cosine x, which is just going to be sine x. And then if we look at a negative sine x, the antiderivative of negative sine x will just be cosine x. And again, that's going to be evaluated from 0 to pi over 4. Over here, again, the antiderivative of sine x should be a negative cosine x. And then the antiderivative of a negative cosine x will be a negative sine x from pi over 4 to pi over 2. So we could just start to substitute this in. So we're going to get sine of pi over 4 plus cosine of pi over 4 minus, now this is going to be a lot to write out, we'll do sine of 0 plus cosine of 0. So that's all just for the first one. Plus the opposite of cosine of pi over 2 minus sine of pi over 2 minus the opposite of cosine of pi over 4 minus sine of pi over 4. So take a look at everything I have written out here. Make sure you see where it's all coming from. All right, so sine of pi over 4, if you need to get out a unit circle or bring up an image of the unit circle, this is what you need to be able to look at and understand. Sine of pi over 4 is radical 2 over 2. So is cosine. Minus sine of 0 is 0, but cosine of 0 is 1. The opposite of cosine of pi over 2, cosine of pi over 2 is just 0. Minus sine of pi over 2, sine of pi over 2 is 1, so minus 1. Minus the opposite of cosine of pi over 4, so that's a negative radical 2 over 2. Minus sine of pi over 4, which is radical 2 over 2. Let's go through and just combine our like terms. If I were to add these two together, I would have 2 radical 2 over 2. This just becomes a minus 1. Over here, I get plus a negative 1 minus a negative 2 radical 2 over 2. So here is just going to turn into a radical 2 minus 1. Here, I'm just going to write it as another minus 1. And then this becomes plus a radical 2. So finally, I end up with 2 radical 2 minus 2 square units. So that problem was pretty lengthy, but still make sure you understand the parts to it, go back over it. All right, so for our next two examples, we're going to switch gears a little bit. Go ahead and pause the video and copy this down. So some regions are best treated by regarding x as a function of y. So we're switching things around. So rather than looking at a curve that's above another one, we're going to look from the left to the right. We're looking at a curve that's to the right. So we go the rightmost curve minus the leftmost curve. So if a region is bounded by curves with equations x equals f of y or x equals g of y, then we'll have horizontal lines y equals c and y equals d, where f and g are still continuous. And f of y will show up if it's greater than or equal to g of y. F of y will be the rightmost curve and g of y will be to the left. For all values y between c and d, then its area is given as this integral, the integral from c to d of f of y minus g of y dy. So go ahead and copy this example down. There's a little bit more work involved. So what we want to do is we want to rearrange this and solve for x in terms of y. So let's start with y is equal to x minus 1. I want to add 1 to both sides, so I'll write it this way: x is equal to y plus 1. And then over here, if we have y squared is equal to 2x plus 6, I want to solve for x. I'll say 2x is equal to y squared minus 6. And then x is equal to 1/2 y squared minus 3. I just divided everything up there by 2. But in order to graph, we're still going to graph the way it looks. So it's going to be a lot easier to graph this version of the equation. And then for the y squared is equal to 2x plus 6, I'm actually going to take the square root. This is just to help me graph. So y is going to equal plus or minus the square root of 2x plus 6. Which is y is equal to plus or minus square root of 2 times the quantity x plus 3. For this, we could kind of look at it this way, but to be honest, it is actually going to be a little bit easier because it's a quadratic to think of it this way. So even though I have it written out here, we'll kind of compare when we're done. So let's go ahead and graph y is equal to x minus 1. If you need to draw out this coordinate plane. All right, so y is equal to x minus 1 starts right here. And then we have a slope of 1. And we'll go ahead and label that. All right, so looking at x is equal to 1/2 y squared minus 3. This is the plus or minus the square root is going to be half of a parabola, the upper half with the positive square root, and then the lower half. But still, it's a little complicated looking at it like this. So if we were to look at it as x equals 1/2 y squared minus 3, this is just going to become a sideways parabola. And normally we would have a y-intercept if that said y is equal to 1/2 x squared minus 3. We'd start down here at -3, but we're going to start right here. And you could pick different y values if it helps. So when y is 0, x is going to be -3. We could say when y is, let's make it 2. So if I substituted in a 2 here, 2 squared is 4. Half of 4 is 2. And then we get a -3. So 2 minus 3 is going to give me a -1. So it means x is -1 and y is 2. Same thing if y is -2, so we're going to be right here. And again, just to get this graphed, I'm just picking different points. Now we could jump to when y is 4. 4 squared is going to give me 16. Half of 16 is 8. 8 minus 3 is 5. So when y is 4, x is 5. And then we can also look at -5. So when y is -4, x is still going to be 5. All right, so this is our sideways parabola. All right, so we have a curve that looks like this. All right, so rather than looking for the distance between the x values here, we're looking for the points of intersections, the y values. So we have a point of intersection right here when y is -2, and then we go up here to where y is 4. So remember, it's y equals c to y equals d. So this is what we're looking at. What we could also do is find the y values of the points of intersection. So in this case, I'm going to set this version equal to this version right here. Actually, let me take that back. We want this version equal to this version because we'll just set the y plus 1 equal to 1/2 y squared minus 3 just to verify. So I'm going to get everything over to one side. So I'll have 1/2 y squared minus 1, or minus y rather. And if I subtract 1 from the -3, I get a -4. Make this a little bit easier to work with, I'm going to double everything. So 2 times 0 is 0. If I double this, I'm just going to have a y squared minus a 2y minus 8. And we'll factor this into a y minus 4 and a y plus 2. Solving for y for each one. So y would equal 4 and y would equal -2. So when I go to set up my area function, this is going to be the integral from -2 to 4. So what I'm trying to do here is find the area of this shaded region. But if we could look, rather than looking for top minus bottom, because that gets a little too complicated here, we could do right minus left. So if I go to set this up, and then right here, this is x equals 1/2 y squared minus 3. This one I'm just going to rewrite as x equals y plus 1. All right, so my rightmost curve in terms of y is going to be the y plus 1. Minus my leftmost curve is this 1/2 y squared minus 3. So I have to keep that in parentheses. And we'll say dy. And then we can go ahead and simplify. So I have y plus 1 minus 1/2 y squared plus 3. Combine the constants here. We could rewrite this as well. We'll put the -1/2 y squared first. Plus y. And we'll get a plus 4. Now we can take the antiderivative here. So we're going to get a -1/2 times y cubed over 3 plus y squared over 2 plus 4y. So we could say this is really -1/6. 4 cubed will give us 64 plus 1/2. 4 squared will give us 16, then plus 16. Then we have to be careful here. We're going to substitute in a -2. So I'm going to write this as a -1/6. -2 cubed will give me a -8. And then -2 squared will give me a +4. So 4 over 2 is going to give me a +2. And then 4 times -2 will give me a -8. -64/6, we could write this as -32/3. See if that helps us along the way. And then 1/2 of 16 will be +8 plus 16 will give me a +24. Over here, this will give me a +8/6 or +4/3. So if we subtract that, I'll still keep it in here. So we're going to get 8/6 or 4/3. 2 minus 8 will give me a -6. So if I take -32/3 minus a 4/3, that's going to be -36/3 or a -9. sorry, negative 12. And then this becomes 24 plus 6, which is 30, finally giving us 18 square units. All right, so this is showing us where our functions are getting a little more complex, but we can solve the equations for x in terms of y and try it sort of sideways here. That's what this problem was illustrating. Let's take a look at one more. Find the area enclosed by the given curves x equals 1 minus y squared and x equals y squared minus 1. So this is a little bit easier. They're already solved for x in terms of y. But let's go ahead and set them equal to each other to find the y values of the points of intersection. So we'll say 1 minus y squared equals y squared minus 1. Let's bring everything over to the right. So we're going to get a 2y squared minus a 2. We could factor out a 2, and we have y squared minus 1. So really 2, if we set that equal to 0, that doesn't make any sense. So y squared is going to equal a 1. Y squared minus 1 equals 0, so y squared equals 1. Therefore, y equals plus or minus 1. So if we were to graph x is equal to 1 minus y squared, we could think of this as negative y squared plus 1. So what this means is if y is 0, x is 1, this is going to open left. So I'm actually going to count up 1 over 1 to the left. Because if x is 0, y is going to equal a plus or minus 1, which is what we found out over here. And then sort of just reverse 2. If I counted up 2, I'm going to go over 4. Or if we said y is equal to 2, we're going to get a negative 3. Or if y is equal to negative 2, we'll also get a negative 3. And that should be enough to graph this. All right, so here is x is equal to 1 minus y squared. Looking at x is equal to y squared minus 1, just the opposite. This is going to open to the right. Our x-intercept when y is 0, x is negative 1. When y is 1 or negative 1, we're going to get a 0, so we're going to cross here and here. When y is 2, we're going to get a positive 3. And then that should be enough to go this way. All right, so if you notice, these are our y values of the points of intersection. So we are trying to find the shaded region between here. So see how it is still a little bit easier if we go the rightmost curve minus the leftmost curve. So again, I want to label this. This is x is equal to y, or 1 minus y squared. Over here we have x is equal to y squared minus 1. All right, so if we set this up, now there's also more than one way to look at this, especially if there's symmetry, but I just want to keep this pretty basic, following the layout that I had 2 pages ago. So our area is going to be the integral from negative 1 to 1. Our rightmost curve is going to be 1 minus y squared, minus our leftmost curve is y squared minus 1. We need that in parentheses, dy, and then we'll go ahead and combine like terms. We have 1 minus y squared plus 1. Can combine the 1's and the y squared, so we're going to get a negative 2y squared plus 2. Take the antiderivative of that. So we're going to get a negative 2 times y cubed over 3. So I could just put this like negative 2/3 y cubed plus a 2y from negative 1 to 1. Substituting in the 1 first. 1 cubed is 1, so we just get a negative 2/3. 2 times 1 is 2. Substituting in a negative 1. Negative 1 cubed is negative 1, so a negative 1 times negative 2/3 will give us a positive 2/3, and then we'll get a minus 2. So here we're going to get a negative 2/3 plus 2 minus 2/3 plus 2. So we'll get a 4 minus 4/3. 4 is the same as 12/3, so 12/3 minus 4/3 will give us 8/3 square units. Right, so that is section 5.1. Again, maybe take a couple more times to go through these examples. Email me if you have any questions.